This project, called GreenStreaming, is about how to reduce the electricity cost for video streaming systems. We first give a brief background of this project, and then we will show a demo. Internet-scale services like Google Search and YouTube are usually supported by multiple data centers. These data centers consume a huge amount of electricity and thus bring large energy cost to the service providers. For example, in 2010, Google used more than 2 million megawatt hours and was about $140 million. So this scale of energy consumption is equal to that of 200,000 households in the States and nearly 2 million households in China. Service providers like Facebook, Microsoft all have tens of millions of dollars energy costs each year. All of these providers have been beginning to reduce their energy cost. We propose a geographical load balancing or GLB-based approach to reduce the energy cost. This approach is motivated by two observations. First, service providers usually have their data centers geographically distributed in different regions. For example, Google has its data center located in 10 different US states. This figure illustrates 6 major data centers of Google. The second observation is the different dynamics of regional electricity markets. For example, when the electricity price in California is $20 per megawatt hour, the price in Texas may be $30 per megawatt hour. This spatial diversity of electricity price motivates the geographical load balancing. The core idea is to assign more user requests or workloads to data centers with lower electricity price, and turn down or partly turn down the servers in data centers with higher electricity price. Geographical load balancing is useful for many applications. In this demo, we show how to leverage GLB framework to reduce energy cost, using video streaming system as example. We use the following demo to show 3 key points. The first is that GreenStreaming reduces energy cost while maintaining video quality. The second point is that GreenStreaming prefers to assign requests to data centers with lower electricity price. The third point shows the effect of bandwidth on the video quality. We built a small prototype testbed to demonstrate the effectiveness of GreenStreaming. We used the left 3 machines to emulate 3 data centers in 3 different locations, and used the rightmost one to generate traffic from the clients. So let's go to the demo. The top left figure shows the real-time electricity price of the 3 data centers. The blue line for data center 1, green for data center 2, and yellow for data center 3. This demo emulates a slotted timeline, and the electricity price varies over time slots. The bottom left figure shows a comparison on the video quality and cost between our method and an existing method. The existing method always first assigns users' requests to data centers with the largest bandwidth. For the cost comparison figures, the top one is for the accumulated cost over time, and the bottom one is for the instant cost of each time slot. All figures in this demo are dynamically plotted over time slots. We have SSH'd to the 3 data centers, and the terminal is used to change their bandwidth. Let's move to the first point. GreenStreaming reduces energy cost while maintaining the video quality. Initially, the 3 data centers' bandwidth are all set to 10,000 kilobits per second. Both methods have the highest video quality, 1080p, as shown in the quality comparison figures. But our method has lower energy cost according to the cost comparison figures. Now we change the bandwidth of data center 3 to 7,000 kilobits per second. Both methods have no quality change. Then we change data center 1's bandwidth to 7,000 kilobits per second. No quality change. And then change it to 3,000 kilobits per second. Also no quality change. We now reduce data center 2's bandwidth to 7,000 kilobits per second. Both methods degrade to a lower video quality, 480p. We further reduce both data center 2 and 3's bandwidth to 3000 kilobits per second. Both methods degrade to the lowest video quality, 240p. Finally, we set all three data centers' bandwidth to the initial value, 10,000 kilobits per second. Both methods return to 1080p, the highest quality. Now, from the quality and cost comparison figures, we can see that our method never has a lower quality than the existing method, and our method's energy cost is much lower. Let's move to the second point. GreenStreaming prefers to assign requests to data centers with lower electricity price and enough bandwidth. This new panel shows the video playing information of a client. It has three figures. The top figure shows the real-time downloading speed of each video chunk. The medium figure shows which of the three data centers is currently serving the client. The bottom figure shows the current video quality. Now from the middle figure, we can see that data center 2, who has the lowest electricity price, is serving the client, though all data centers have enough bandwidth. Finally, we show the effect of bandwidth on the video quality. Please note that all data centers now have a bandwidth of 10,000 kilobits per second. We first reduce data center 2's bandwidth to 7,000 kilobits per second. The client requests go to data center 3. We then change its bandwidth to 3,000 kilobits per second. The client requests go to data center 1, though the data center has the highest electricity price. This result indicates that our method's first priority is to guarantee high video quality, and then its cost reduction. We further reduce data center 1's bandwidth to 3,000 kilobits per second. After this, the client requests will return to data center 2, because the data center currently has the largest bandwidth, 7,000 kilobits per second. The video quality degrades accordingly to 360p. We further reduce data center 2's bandwidth to 3,000 kilobits per second. All data centers have very low bandwidth, and the video quality degrades to the lowest, 240p. Now, see what will happen next. Yes, as shown in the middle figure, the client side keeps moving around the three data centers and searching if there are data centers with better bandwidth. After we increase the bandwidth of data center 2, the client requests go back to this data center. Even though we increases the bandwidth of the other two data centers to a much higher bandwidth, say 12,000 and 14,000 kilobits per second respectively, the client still sticks to the data center 2. This again confirms that our method prefers to assign user requests to data centers with lower electricity and enough bandwidth. Not once, only with the largest bandwidth. Thank you for watching our demo.